Voltage standing wave ratio. This is our topic. In short, we call it VSWR. We know that the performance of the transmission line can be determined by using characteristic, that is Z0 and ZL. Here Z0 is called a characteristic impedance and ZL is the load impedance. Both are the complex impedance. Many times it is not possible to determine the performance characteristic of the transmission line. In that case, we use the standing wave ratio to determine the performance characteristics, that is Z0 and ZL. And to determine the voltage standing wave ratio, we have to measure the voltage amplitude, that having maximum voltage amplitude and minimum voltage amplitude, and both are the function of positions within the transmission line. And to determine voltage amplitude in the form of maximum and minimum value, we use an apparatus. This apparatus is a type of slotted line which is generally a lossless coaxial transmission line having inner conductor and outer conductor. Between the inner conductor and outer conductor there is a gap. This gap is called a longitudinal gap, which is along the entire transmission length. Now through this longitudinal gap we insert a voltage probe to measure the voltage amplitude in the form of maximum value and minimum value, that is between the inner conductor and outer conductor. So after measuring the maximum voltage amplitude and minimum voltage amplitude, we can determine the voltage standing wave ratio, that is denoted by small s. So the ratio, that is maximum voltage amplitude upon minimum voltage amplitude, is called a voltage standing wave ratio. And now with the help of this voltage standing wave ratio, we can determine the line performance, that is the transmission line performance characteristic, which is Z0 and ZL. Now we talk about standing wave. What is standing wave? When two voltage waves having equal frequencies and amplitude propagate in opposite direction on a lossless transmission line, then we recognize a standing wave. So we can say that the standing wave is recognized when two voltage waves are propagate in opposite direction having equal frequencies and amplitude. And here we use a lossless transmission line and the condition is R equals to G equals to 0. And here our object is to determine the total voltage as a function of time and position, that is real instantaneous form of a voltage wave. For this we first consider a voltage as a function of position, and here we know that the propagation is towards z direction, so we consider a total voltage as a function of position, that is z, and it is written as V suffix st function of z. Here T stands for total voltage and S stands for sinusoidal 1 and Z is the position. So it is equals to V naught e to power minus j beta z plus V naught e to power plus j beta z. Here minus sign in the exponent is for forward propagation and positive sign in the exponent is for backward propagation. So here we see that between the two exponent term there is a positive sign. So we can convert it into a cos form. For this we multiply and divide by 2 and this become a formula of the cos beta z. So the total voltage as a function of position is equals to 2V naught cos beta z. Now we can convert this equation into real instantaneous form of the voltage. For this we first multiply by a time factor, that is e to power j omega t, and then we take a real part. So after multiplying by e to power j omega t and taking a real part, we get 2V naught cos beta z into cos omega t. We get cos omega t as a real term in e to power j omega t. So from here we find that the amplitude amplitude of the total voltage varies as cos beta z, whereas the total voltage oscillate in time as cos omega t. So this real instantaneous form of the total voltage is called a standing wave. The standing wave is written as 2v0 cos beta z into cos omega t. Here cos beta z is responsible for variation of amplitude, whereas cos omega t is responsible for the oscillation in time. And this equation is called a standing wave equation. Now we note the points. The first point is, in case of matched impedance, that is ZL equals to Z0, there is no reflection. Here the reflection coefficient capital tau is equals to 0. In this case, the apparatus, which is in the form of voltage probe, indicates the same voltage amplitude at every point of the transmission line. In this case, there is no standing wave, because the standing wave is recognized when two voltage wave of equal frequency travel in opposite direction on a lossless transmission line. And since here there is no reflection, because there is a reflection coefficient tau equals to 0 due to matched impedance, that is Z equals to Z0, so there is no standing wave. And the second point is, the apparatus or device that is in the form of slotted line is terminated by open circuit or short circuit. In that case, the total voltage of the transmission line is the standing wave that is given by above equation. Here, the slotted line is terminated by open circuit or short circuit, that is a pure imaginary load impedance. In that case, we get a standing wave. So here we conclude that when the transmission line is matched, that is matched impedance, in that case there is no standing wave, and otherwise we recognize a standing wave when the slotted line is terminated by open circuit or short circuit. Now our objective is to determine the specific form of the total voltage, that is in the form of maximum amplitude voltage and minimum amplitude voltage, to determine the voltage standing wave ratio. For this, we consider a forward propagating wave and backward propagating wave within a slotted line, that is the apparatus which is used to determine the voltage standing wave ratio. So here we consider a apparatus that is a type of slotted line which is a lossless coaxial transmission line having a longitudinal gap. And in this slotted line, we consider a load impedance ZL that is situated at Z equals to 0, because we consider the propagation is towards Z direction. So here we consider a load impedance at Z equals to 0, and the region Z less than 0 is occupy a transmission line, that is a negative value of Z. So here total voltage, that is a function of Z, is written in terms of forward propagating wave and backward propagating wave, and both having equal magnitude and frequency, so as to determine the standing wave. So here the total voltage wave function of Z is equals to V0 e to power minus j beta Z plus V0 e to power j beta Z. Here the second term is for backward propagation, and in case of backward propagation we talk about reflection coefficient. The reflection coefficient is the ratio of the reflected voltage amplitude upon incident voltage amplitude, which is tau, capital tau, and capital tau is in polar form having magnitude mod of tau and phase phi. So in a backward propagating term we have a magnitude amplitude V0, that is V0 R. So in place of V0 R we can write mod of tau e to power j phi. So the total voltage as a function of Z is equals to V0 within bracket e to power minus j beta Z plus mod of tau e to power j within bracket beta Z plus phi. Here phi is introduced by using a reflection coefficient capital tau, that is the phase of the reflection coefficient. Now the next step is, to make the calculation easy, we multiply and divide by e to power j phi by 2. So we take e to power minus j phi by 2 within the bracket. So from here the second term is having three exponent term. First is e to power j beta z, second is e to power j phi, and third is e to power minus j phi by 2. So we combine the exponent having phi and it become e to power plus j phi by 2. Next is we add and subtract by v naught within bracket 1 minus mod of tau e to power minus j beta z. We add and subtract this term in the above equation and simplify it. After simplification, we get v naught within bracket 1 minus mod of tau e to power minus j beta z plus mod tau v naught e to power minus j beta z plus e to power j phi by 2 into e to power j phi by 2 into e to power j beta z. This we get after cancelling some terms and taking some common terms. Now in a second term we take e to power j phi by 2 as a common. So after taking e to power j phi by 2 common, we get within bracket e to power minus j beta z upon e to power j phi by 2 plus e to power j beta z into e to power j phi by 2. So there is a positive sign between the exponent term, so it becomes a formula of the cos. For this we multiply and divide by 2. And we get a total voltage that is a function of z equals to v naught 1 plus mod of tau e to power minus j beta z plus 2 v naught mod of tau e to power j phi by 2 into cos beta z plus phi by 2. Now to determine the real instantaneous form of the voltage, that is a function of z and time t. This equation is a function of z only, and to determine a real instantaneous form we have to multiply by a time factor e to power j omega t and then we take a real term. So the first is v naught 1 minus mod tau cos omega t minus beta z, and the second is 2 v naught mod of tau e cos omega t plus phi by 2 into cos beta z plus phi by 2. Here the first term is called a travelling wave with amplitude v naught 1 minus mod of tau, and the second term is called a standing wave. It has an amplitude of 2 v naught mod of tau. Because we know that in a standing wave the oscillation is due to cos omega t plus phi by 2, that is due to the time, and the variation of the amplitude is due to the cos beta z plus phi by 2, that is due to the position, that is z. So we can say that the portion of incident wave that reflects and back propagates in a slotted line interfaces with the equivalent portion of the incident wave to form standing wave. Now the next step is we have to determine the maximum amplitude and minimum amplitude of this real instantaneous form of the total voltage. To determine the maximum amplitude, we add the amplitude of the travelling wave and amplitude of the standing wave. The amplitude of the travelling wave is v naught 1 minus mod of tau, and the amplitude of the standing wave is 2 v naught mod of tau. So after adding these two amplitude we get a maximum amplitude, that is 1 plus mod of tau into v naught. Similarly we can determine the minimum amplitude. Here the minimum amplitude is the amplitude of the travelling wave only, because here the amplitude of the standing wave is 0, because we know that the standing wave is recognized when a portion of the incident wave is reflected back and interfere with the same portion of the incident wave, we get a standing wave. So the maximum amplitude is the combination of amplitude of the travelling wave plus amplitude of the standing wave, which is 1 plus mod of tau into v naught, and the minimum amplitude is only the amplitude of the travelling wave, that is v naught 1 minus mod of tau. And the voltage standing wave ratio is the ratio of the maximum amplitude upon minimum amplitude. After taking the ratio, we get a voltage standing wave ratio that is small s equals to 1 plus mod of tau upon 1 minus mod of tau. So the voltage standing wave ratio is equals to 1 plus mod tau upon 1 minus mod tau. That is the ratio of the maximum amplitude upon minimum amplitude. And this form is a specific form of the total voltage in terms of voltage standing wave ratio. These maximum and minimum voltage amplitude is also correct for a total voltage that is a function of Z. Here the total voltage that is a function of Z and having a minimum amplitude is V0 1 minus mod of tau, and the maximum amplitude is V0 1 plus mod of tau. Now we plot the maximum amplitude and minimum amplitude that is a function of Z only, and here we consider the load impedance is at Z equals to 0 and the transmission line occupy a negative value of Z. So here we plot a mod of V suffix st versus Z, that is the amplitude versus position, and here in this region, that is for Z less than 0, that is for a lossless transmission line, and in this region there is a standing wave. So here we consider a standing wave and it has a maximum amplitude and minimum amplitude. The minimum amplitude is 1 minus mod of tau V0 and the maximum amplitude is 1 plus mod of tau V0. And here we consider a total voltage that is a function of Z only. Now to get a minimum amplitude, we put minus beta Z is equals to beta Z plus phi plus pi. Here pi is introduced in a reflected wave because when the incident wave is reflected back, there is a 180 degree phase shift, so that we introduce a pi with the reflected phase. So with the help of this condition we get a minimum amplitude. The minimum amplitude is obtained at Z minimum and its value is minus 1 upon 2 beta into phi plus pi. And to get a maximum amplitude we use Z max, that is equals to minus 1 upon 2 beta into phi, because there is a phase difference of pi between maximum amplitude and minimum amplitude. So the maximum amplitude is obtained at minus phi upon 2 beta, next is minus 1 upon 2 beta into phi plus 2 pi, and then minus 1 upon 2 beta phi plus 4 pi, and then minus 1 upon 2 beta phi plus 6 pi. Similarly, the minimum amplitude is obtained at minus 1 upon 2 beta phi plus pi, then minus 1 upon 2 beta phi plus 3 pi, and minus 1 upon 2 beta phi plus 5 pi, and so on. So we can say that the minimum position having a odd integer multiple. So in general we can write Z minimum is equals to minus 1 upon 2 beta into phi plus 2m plus 1 into pi, where m is any positive value including 0. Similarly, Z max is equals to minus 1 upon 2 beta into phi plus 2m pi. And here we note a point. The reflection coefficient is the ratio of ZL minus Z0 upon ZL plus Z0, and in polar form it has a magnitude and phase, and here phase depend upon the load impedance ZL. In a transmission line, if the load impedance is short circuit, in that case the load impedance is 0, and this is a requirement of 0 voltage. When the voltage is 0 at the load side, the load impedance is 0, and we call it null occurrence because here the load impedance is 0, and in this case there is 180 degree phase shift, and due to this 180 degree phase shift there occur a standing wave. So the standing wave recognized when the load impedance is 0 and the phase phi is equals to pi. So when the load impedance is less than the characteristic impedance, in this case the phase is pi, that is a 180 degree phase shift, and in this case the standing wave recognized. And when the load impedance is greater than the characteristic impedance, in this case the phase shift is 0, and in this case there is no standing wave. So this is about the voltage standing wave ratio, which is used to determine the transmission line characteristic when there is a problem in determining the Z0 and ZL.